Okay. I don't remember the host key for some reason, so I can't.
I think I have to look and see if I can spot where any mistakes. Filling
Do you
the
need
door
the
was.
host key?
I don't think so. I think the assets will go to your email, right?
Yes.
So we're good.
Do you want to turn the volume down?
Yeah, I'm gonna turn the volume down on my phone.
You gotta keep the audience force muted.
Be able to hear me. Oh, we're good now.
Or do you do the audience?
I don't know how to mute the audience.
I think you hit deafen. On yourself, right?
I can mute myself, but then it wouldn't be able to hear me talk.
That would be a problem.
I think it'll be all right. I think yeah.
Just click participants in the bottom menu, then click mute all.
I'm the only one in the meeting right now, so
Do you want me to do it?
Yeah. yeah, you're muted, so it's fine. Can you hear it? Like, can you hear me? Thanks, man. I'm all.
Yeah.
Audience.
Hmm?
You can do audience.
Okay. Participants. Oh, I can just tap to mute and like there can. Oh, I can't. I'm not the host. Sorry. I don't need to mute the audience. I'm not worried about it.
You want.
Just remind me of it. Once you say it, I'm gonna remember.
It's 10:32.
That's it. 10, 15, 19. I like your hat. His hat says H5 this one. It's perfect. Relevant.
Not as often as I used to. So thoughts.
Run out of space for people. I don't think the people say they were gonna come. I lined some extra chairs up in the back. If need be, they're standing room. We put them in nosebleeds out there.
So I got your early.
Charging the park in Nebraska.
Like scream it like outside, not like come late. It's like,
Oh yeah, like how at concerts they have speakers in the bathroom.
oh yeah.
There was, I don't remember where it was, but I went to one place that was like a, almost like an opera house, and they had TVs in the, like in the lobby, if you left, that you could just watch stuff on.
Go to the opera house and watch Family Guy instead.
That's some of the servers here.
any opera houses nearby?
I don't think so. Well, there's the, whatever's on the strip right there,
The
but that's,
varsity.
yeah, the Varsity.
Oh,
That's not necessarily an opera house, it's more of a, like a theater.
Probably the closest we have.
About the closest thing we had, yeah.
Unless you go to, I think, the MIGMA.
Yeah.
Communication, media arts.
Oh,
Oh.
oh, where they have their musicals and stuff. Like,
That makes sense.
Is that what it's called?
Well, there's two different things. There's like the building for mass comms, media, and then there's Shyrock.
I thought they were the same building.
No,
on a satellites on it.
one's the one that looks like a weird castle, the other one just looks like a regular academic building.
Or you know.
How long have you been going here?
6 years.
Exactly.
I actually had to walk by both of them every day for 5 of those years.
That's okay. Oh, do you have the clicker? No. If that's okay. I can replicate it. Try to ask you about that.
You know, this does seem to be set up in a really nice way where nobody can keep walking in front of you.
Good luck. That was like, and for those that don't get the joke, Ron defended his dissertation yesterday, and the second that he finished, one of the people in the audience got up, walked right in front of him, held his hand up, said "good luck," and walked out. The same guy showed up 10 minutes late, started moving desks around.
One of your committee members.
No, that would be tragic. That would actually be tragic.
Congratulations. So.
Thank you. Yes. Oscar Sonway.
Yeah. It was a little bit more focused than the talk I gave to you, but yeah.
Yes.
Is that your thesis?
Is that my what?
Your thesis?
Yeah, this is a copy of it. Philip has a physical copy of it too behind you.
You might want to put your phone on Gene.
Oh, is it? It's got notification. Y'all can find a seat wherever, but y'all might have to sit in the back row.
I feel like near the front, just so people come in late and there's seats here.
Yeah.
That would probably be smart. Okay. Now I can leave in the middle.
Oh, yeah.
Right in front of the camera.
Not the camera. You clearly never watched Iowa football.
Nope.
The joke of Iowa football is that it's only defense. Like if they score more than 7 points in a game, beautiful.
Does defense score more points than the offense regularly?
Yes.
Okay.
Iowa athletics in general are known for not being attack heavy. They're known for just being sturdy. Do the same thing with basketball. They're doing it this March Madness.
Are they still in? I don't know.
Yeah, they upset #1 seed Florida.
Really?
9 seed Iowa beat 1 seed
Wow.
Florida.
Is that the biggest like upsets like seed-wise or is that sense?
I think that's the biggest upset seed wise. The one benefit of this small room, it doesn't take a lot of people to pack this thing up. It's good for the ego.
Just so you know, I might be getting a medical call that I'll have to step out.
You're all good.
Okay, you go ahead.
If the committee doesn't have room to sit down, I can stay.
I've only got 2 more committee members coming, and there are 4 more chairs, 5 more chairs, 6 more chairs available.
So why your defense is so popular?
I think it's because I am in the two departments.
I was paid to be here, weren't you?
Oh. You weren't supposed to say that loud.
Yeah, the check bounced.
Oh. I'm under the age of 40. You think I write checks? I don't think I've ever owned a checkbook. I don't like because nowadays you can say like, oh, I want a checkbook or I don't when you set up an account. I've never said I need a checkbook. You're
The Shardy's on her way.
Okay, cool.
Excuse.
Europe will be like
You're,
society.
yes.
Yeah.
It is 11 o'clock right now.
It's about 5 seconds off. Oh, unacceptable. Yeah, there's 2 seats here, 1 seat back there, 2 seats here. As long as we have a seat for Europe, we'll be good.
Speaker's bad.
Yes.
Awesome.
Does anyone need paper to take notes? I also have some extra pens and pencils if anyone wants to take notes or play tic-tac-toe.
We're good. We don't take notes, so we're good. We like it.
Anyone else?
Here's questions.
Scratch papers here, take notes, there will be a test afterwards. Worth 100%. And if anyone needs a pen or a pencil, I'm gonna touch your door. There's a blue pen. All right.
You looking?
Not yet. Should I?
No, give
You
it,
can start.
let's give it 2 minutes.
Oh,
I can go around for him, yeah, up to the room.
Oh, here, it's called.
Oh.
Hello? We are 410. In the Neckers building.
Oh,
Okay, Mike's gonna look for you.
Good, that is helpful,
It's
yeah.
lost, all right.
This building is always a maze for everyone. Like every time I have students come for office hours, I'm like, just get to the building and I'll come find.
Painter is worse.
I don't know. Feiner is like 1, 4, and that's it. This building is like 20 different directions.
There's like half doors.
Yeah, Feiner is split in half though, so that
And an ABC.
and yeah, it's got the different wings. We technically have different wings, but no one says like Necker's A 240.
I don't think it's put into the last argument, a little after And school.
It's okay.
It's okay.
Yeah, I can see.
One thing I wanted to ask at the end, if everyone would mind getting together for a picture, both everyone together and then with the committee. This was requested by Shara and the partnership just on Facebook. So if you don't want to be in the picture, you can take the picture out there. That's a resolution. Also, I'm recording this, but I don't think anybody's face is in it.
You have to go in the front, this is for my, this is for my.
And sorry, guys.
Oh, I don't know. Alrighty.
Welcome, everybody, to the oral defense of Jackson Lewis. This is a requirement for Master of Science in Mathematics and Physics. And the first part will be public, as you can see. The second part will be closed door session between the committee and Jackson. So I'll request everyone to leave, and then you can come back for the picture. If you're interested, I'll take a picture before as Jackson wanted. Thank you.
Alrighty. Howdy, everyone. Everyone doing okay? Everyone hear and see clearly. Awesome. So, as you just said, my name is Jackson Lewis. I'm here doing my oral defense of my master's thesis in mathematics and physics. More or less, this thesis delves into the mathematics of representation theory and the physics of quantum mechanics, and doing some cool things with those. Title of my talk is Hyperbolic Angular Momentum, so I'll get into what that means. I'm going to start first with the harmonic oscillator, quantum mechanics, and talk about some of the algebra related to operator methods. I'm going to do the same thing with angular momentum, studying it symmetrically, like its symmetry properties, and talking about its operator methods. Then I'm going to combine those together into the Jordan map, and that's going to yield what we call hyperbolic angular momentum. So we'll talk about that, study it a bit, introduce some things with it, and then apply hyperbolic angular momentum to addition of angular momentum to get a cool result of a standard argument, but a not standard proof for it. And then we'll do some conclusion. So first, we're going to talk about the harmonic oscillator. Classically, this is modeled as a mass on a spring wiggling back and forth. We're talking in quantum mechanics, so we want to really talk about the energy of the system here. Typically, this is just the sum of kinetic and potential energy. For a system such as this, that's just going to be 1/2 mv squared and 1/2 kx squared. I can also rewrite this in terms of momentum and position. So 1/2m gets factored out, and I've got this p squared and then m omega x quantity squared, where omega is the angular frequency of the spring, given at the bottom right there. We want to motivate this in quantum mechanics by replacing all of our physical observable variables with Hermitian operators on a linear space in some basis. So I could pick, for instance, the position basis. Here, my x variable, my position variable, is just multiplication by x. My momentum variable becomes minus IH bar, and then the derivative operator. And they're defined in such a way that they satisfy this commutation relation. This just means on a given axis, I can't simultaneously measure position and momentum with perfect accuracy. I'll have some sort of uncertainty between those positions. And this momentum operator comes from the fact that momentum is the generator of changing position. So change of position, derivative operator generated by momentum. Right. So I can use this to rewrite our energy as what is known as the Hamiltonian operator. So this is a linear operator that will measure out the energy. I can more or less factor this into A and A dagger. These are also going to be operators. It's kind of like factoring A squared plus B squared into A plus IB and A minus IB. So I do that, or at least suggest these operators. Now I want to look at what their product are. So if I do A with A dagger, I get this right here. We notice that this is the Hamiltonian that I was mentioning earlier with a scaled factor out front. And I get this extra term here that comes from the, you can't see that at all. Comes from the commutation Px minus Xp. So it's the commutation relation, and I get an extra factor out there. Simplifying that down, I'm just getting 1 over h bar omega times my Hamiltonian operator, and then plus 1/2. So it's more or less proportional to the Hamiltonian operator. I'm just scaling it and shifting it a bit. And if I multiply in the opposite direction, I'll get the opposite commutation relation of x and p, so I'll get a minus 1/2 instead. And then with these constructions, we note the commutation relation of A and A dagger. If you didn't take anything away from the past 5 or so minutes, this is what you should take away. The commutation relation of A and A dagger is 1. That's what's defining this algebra here. We want to now talk about this in an energy basis. So we're in a position basis. I can motivate this in an energy basis, and that will give us a discrete structure. So I'm going to write this as a eigenvalue equation. So the Hamiltonian operator acts on this funny parenthesis looking E. That means that's a vector, or specifically a function in a function space. So E is an energy basis state, and then E by itself, not in the parentheses, is the measured energy value, or the eigenvalue of H on this basis. So if I measure the energy of A dagger acting on E, or A acting on E, I can go through, do some computations, and show that A dagger is going to raise the measured energy, and A is going to lower the measured energy. Because they raise and lower, I'm going to aptly call them the raising and lowering operators. And note that they raise not by an arbitrary value, but by fixed units of h bar omega. They're raising by integral values, raising or lowering. Because they're raising in these discrete values, I can give a discrete basis for it. So there's not just any arbitrary energy value, there's fixed in our energy values. So a basis state that would read the nth energy value, for simplicity of notation, I'm just going to call it n. The number operator I then define acts on this to just read out whatever that value of n is. So another eigenvalue equation, n, the operator acting on the vector, reads out the value n. And I also have the raising and lowering operators. I see that n goes to n plus 1 when raising, n goes to n minus 1 when lowering, and those coefficients out front are normalization coefficients. This n plus 1 comes from the fact that A dagger A, or this comes from A dagger A is 1, this comes from A dagger is n plus 1. So that's where those come from when I normalize them. But what are the allowed values of n? Well, first, I'm going to take the expectation value of n. It's just measuring it in between the dual vector and the vector itself. And I get just the value of n, since this is an orthonormal basis, given that it's an eigenbasis of a normal operator. This bottom equation, however, is equivalent. Note that n, my construction, was given as A dagger A, but this is just the squared magnitude of A dagger on n. Since it's a square magnitude, it's non-negative. And since these equations are equal, n has to be non-negative itself. But are there other restrictions on n? Well, what if we consider n to be 1/2, like the state 1/2, and we lower it? So A acting on this 1/2 state, I'll get the square root of 1/2 out front, but what I'm mainly concerned with is the fact that I got a negative 1/2 state. But one slide before, I said that I can't have n less than 0. So this is an invalid state, so I have to have non-negative integers. When it gets to 0, the rest of the states are 0, so that's the terminating state. Otherwise, everything has to be a whole integer because it can slip under that 0 state and start going down negative with unallowed states. So the summary of the results so far, the most important thing, in my opinion, A dagger A is 1. That'll give us a structure that's important. A lowers the state. A dagger raises the state. N measures the state. And the allowed values that label the state are non-negative integers. From now on, we're going to use natural units. So we're going to set h bar equal to 1. This is perfectly allowed in a common physics convention. It just means I don't have to write h bar for the rest of this. Now we can talk about angular momentum in a similar light. So in quantum mechanics, we're defining a system of angular momentum as a set of 3 operators, almost like a vector, that satisfy this commutation relation. It's just saying that if I measure angular momentum in one direction and then measure it in another direction, if those are orthogonal directions, I'll get some sort of component in the third direction. This epsilon ijk here, it's the Levi-Civita symbol, It just means that if it's a cyclic permutation, if it's even, I get a 1. If it's an odd permutation, I get a -1. And if indices repeat, I get 0. From these J1, J2, J3, I want to construct what's called the Casimir invariant. This just is an operator constructed as some combination of these basis elements such that it commutes with everything. So I see here J squared will commute with J1, J2, or J3. You can go through and show that explicitly based on the thesis. And by convention, we're going to fix a reference axis. Since I can't simultaneously measure angular momentum in multiple axes at once without some sort of uncertainty, I'm going to just fix what is more or less a reference axis and talk about that. By convention, we pick J3, that's like angular momentum in the z-axis, and those commute. And because they commute and are normal operators, they share an eigenbasis. The proof of this is rather long and tedious, but it's provided in the appendix of the thesis. So because they share an eigenbasis, I'm going to list an eigenbasis, and I label it by the labels of the eigenvalues of the operators. So specifically, J squared on this doesn't change the state. I just go to J times J plus 1 out front. And J3 doesn't change the state. I just read out the M value. J is restricted to values of non-negative half integers, and that can be shown explicitly. And M is restricted to be from -J to +J in integer steps. Again, all of this is derived explicitly in the thesis. We're also now going to define operators that ladder the spectrum or the eigenvalues of J3. So let J plus be J1 plus IJ2, J minus J1 minus IJ2. They commute with J3 in the following ways. Those apt on representation theory of Lie algebras might recognize this as the defining commutations of SU2. Makes sense that rotation algebra defines angular momentum. And these J plus and minus acting on my eigenbasis give me some sort of normalization coefficient out front with a raised M value for J plus or a lowered M value for J minus. Because they raise or lower, I also aptly name these a raising operator and a lowering operator. And like I said, we note that these are the defining commutation relations of SU2. The group SU2 describes isometries of rotations in 3 dimensions. So the algebra talks about the algebra of the generators of this group. Now we want to put these ideas together in what's called the Jordan map. Our reference for this is the connection between symmetric and linear groups and the many-body problem. If you try to look this paper up with this title, you will not find it, because before this thesis, this paper did not exist in English. One of the things that I did in this thesis is I went through and translated the whole paper by hand. If you want to see it, it is Appendix C in my thesis. What this paper is saying is that the basis elements of the algebra GLN are functionally equivalent to combinations of the raising and lowering operators for the harmonic oscillator. GLN is the algebra describing the group of invertible linear operators, and we'll see what we're talking about. But because we can represent GLN with these, we can represent Lie subalgebras of GLN as well. So first I want to talk about the basis of GLN. It's any n by n matrix, we'll call it EKL, where K, or there's a 1 in the kth row and L column, and there's zeros everywhere else. I'll give an example specifically for GL2. So 1, 1 has a 1 in the 1/1th position, 1, 2 has a 1 in the 1/2th position, so on and so forth. And then we notice that any 2 by 2 matrix is just a linear combination of these together. So any matrix representation of an element in GLN, this algebra, can be given as just the sum of the coefficients multiplied by the basis elements, right? So like if my matrix is A, B, C, D, it'd be A11, B12, C21, and D22, something like that. And these satisfy the following commutation relations. Specifically, they're real valued. They satisfy this commutation relation, and if I sum up the diagonal entries, I get the dimension of like GL2, for instance, I get 2 for that diagonal. And then this delta ij is the Kronecker delta, 0 if they're different, 1 if they're the same. Now we recall the harmonic oscillator operators. We had the lowering operator, the raising operator, and n itself. And the thing I said was the most important, A dagger is 1. For multiple disjoint harmonic oscillators, that's those that don't interact with each other, Aj dagger is delta Ij. So it's 0 if they're not on the same oscillator, and it's 1 if they're on the same oscillator. And each individual oscillator has its own number operator associated with it. I'll say Ni is Ai dagger Ai. I'm not implying summation here. I'm just restricting it to the ith oscillator. And the total number given from all the oscillators together is just the sum of the individual number operators. So if I had k oscillators, it'd be A1 or N1 plus N2 all the way up to Nk. So I'm going to construct the following operator. I'll say AKL is A dagger KAL. So it's the raising operator on the kth oscillator, the lowering operator on the lth oscillator. And it satisfies the same relations as the basis elements did. So 1 prime, 2 prime, 3 prime, it satisfies these same relations. Because of that, it is algebraically functionally equivalent. That means that they play the same role algebraically, they do the same things. So because of this, I can use these operators to represent the least of algebras of GLN. Remember that I said that any element is just the basis elements times the coefficients, so a linear combination of those. But I can replace this Eij with Aij since it's functionally equivalent. I'm just dropping the summation here, so it is implied now. I can then replace Aij with Ai dagger Aj. And note that Xij is just a coefficient. It's the ith jth component of the matrix. So I can move the Ai dagger to the other side. And if we look at this like its summation notation, this looks like a vector times a matrix times a vector. So I can represent it as such. I'll let Y be this column vector of lowering operators. And then for any X, I can say that it's Y dagger, the matrix representation of X, and Y. And I'll give a specific example of this. For instance, if I take the J equals 1/2 irreducible representation of SU2, so this is going to be the 2x2 representation of it, the fundamental representation, I can get matrix representations of J plus, J minus, and J3. Those are explicitly derived in chapter 3 of the thesis. And then I can use these to generate oscillator constructions. So J plus will come out to be A1 dagger A2. We don't have a significant realization of this yet, but we'll get there in a minute. J minus is going to be A2 dagger A1. And J3 is going to be 1/2 and the difference of the number operators. So representing SU2, I've got a construction of J plus, J minus, and J3. And now we want to get a special basis that gives this physical significance, that gives us a theory of angular momentum. And that's where we're going to delve into hyperbolic angular momentum. So our reference here is the paper on angular momentum by Julian Schwinger. This is not an actual paper. It's an article commissioned by the Department of Energy in Oak Ridge, Tennessee. Didn't actually get published, but you can find PDFs of it online. This paper is saying that we can essentially use the Jordan map to construct a theory of angular momentum. He doesn't refer specifically to the Jordan map, but he says that we can use these oscillator constructions to give a theory of angular momentum. Since we're interested in specifically SU2, the least of algebra of GL2, I only need 2 oscillators. So I'm going to say A1 and A2, I'm going to relabel as just A and B. So just kind of, they're very distinct notationally. Then A will have an NA, its own number operator. B will have its own number operator. And the total number operator is the sum of those. So our oscillator representations, I then just rewrite, just relabeling A dagger B, AB dagger, and then 1/2 and the difference of the number operators. Now we're going to consider the tensor product of the bases for the individual oscillators. Mathematicians typically write a tensor product basis like this. Physicists like to write it with a comma in between, like one bracket. Or mathematicians more so will write this as like basis vectors with a tensor product symbol. Or no product in between there. And the action of the oscillators only acts on the component of the oscillator it belongs to. So the components to the A operators will only act on the NA spot. B operators will only act on the NB spot. We recall now the angular momentum eigenstates that we labeled with Jm. I'm going to let NA be the sum of the listed Jm, and B be the difference, and I can solve for J and M respectively. Doing that, I can rewrite Jm in terms of this number basis, so they're equivalent to each other essentially. Jm can be shown to give rise to NA and NB using this construction here. This is J, this is M, and that's just NA. So now I can use this basis, which we call the Schwinger basis, to act these oscillator constructions of the SU2 operators on. So if I act this J plus on here, it's the same thing as A dagger B on NA and B. So I get this coefficient out front, NA goes up and NB goes down. I process this a bit, so I do the NA plus NB, NA minus NB, and then rewrite this in terms of J and M. So we notice this is the exact same coefficient we had out front, and we get a J with a raised M value in our eigenstate. We can do the same thing for J minus, so I'll get my equivalent coefficient out front, and the M value goes down. Slides look similar, but some of the signs change. That's about it. Now we want to introduce a method of visualizing this. So this is one of the things that Yuri contributed heavily to the project because he has just a great gift for being able to visualize literally anything. So first I want to create a grid almost of coordinate points, and each what would be a coordinate here is going to be given as the number basis state. So the coordinate 4, 2, I'm going to give as the basis 4, 2. And recall that M is given as the difference of these. So because of that, I can draw in fixed lines of M on my grid, given as such. Note that they're not bounded below, so they can keep going on up. And I could get negative values here. I just didn't label them for visual simplicity. So each line gives a labeling of M. And we also recall that J plus and J minus ladder the values of M, so they go up M or down M. So I can put J plus on here to go up values of M, and J minus to go down values of M. And then what do I notice? J plus goes up in A dagger, goes down in B, B. We said J plus was A dagger B, and we get J plus as A dagger B. Similarly, J minus gives me A B dagger, goes down in A, up in B. So this visual construction perfectly replicates the oscillator construction of the Jordan map, but just from looking at it. But what about the other diagonal? This diagonal only goes in this direction. The lines are fixed that way, the operators act that way. What if I do it in the other direction? So, by the way. Recall that J is the sum of these NA and NB, so the diagonals are going to go the other direction, like this. And I can suggest operators that go in the other direction. Note that the J values are bounded by the axes. That's what these off diagonal lines are. They'll hit the axis and then they'll terminate. So if I suggest operators in the other direction, maybe I call them K plus and K minus. K's action is going to be up in A and up in B, so A dagger, B dagger, and K minus is down in A and down in B, so A, B. So I've got what looks like ladder operators on J, but I want to act them on the Schwinger basis to see if they really could be ladder operators. I'll notice that K plus acting on here, when I process it like I did J plus, I get some coefficient up front, the M value remains the same, and J plus 1 now, so I've raised J. Similarly for K minus, I'm going to have a coefficient out front, J value goes down and the M value is remaining constant. So it looks like we have a pair of ladder operators on here. This means that these go in between, they jump between the irreducible representations of SU2, rather than sticking in an irreducible representation of SU2 and going within it, like the J plus and J minus ladder operators do. So we had an algebra that was generated by J plus, J minus, and J3. We want to see what happens if we try to generate an algebra with K plus, K minus, and K3. I'll first take the commutation relation of K plus, K minus, process it out a little bit, and I get the negative of something that will always have positive eigenvalues. So because I get the negative of something with positive eigenvalues, I'm going to call this negative 2K3, and then define K3 as follows. So this always has positive eigenvalues. It's not necessarily a requirement, but it's convenient. So with that construction of K3, I get the following commutation relations. These two look like the SU2 commutation relations, but this one gives a negative sign. That means that we have a representation of SU11. These are the defining commutation relations, where that algebra is isomorphic to the algebra SO21. SO21 is the algebra of the group SO21. This is the group of isometries of hyperbolic space in 2+1 dimensions. More specifically, it's known as the Lorentz group, but in 2+1 dimensions. Because we're talking about an algebra that represents isometries on hyperbolic space, we're going to call this hyperbolic angular momentum, thus giving the title of the project. And we can connect this to regular angular momentum using a restriction on it. We denote the invariant of SU11 to be given as this, where K1 is defined as the sum of the ladder operators. K2 is the difference of them scaled out, and K3 would just keep K3. And I can rewrite this invariant using K3, K plus, and K minus. Processing this back into the Schwinger basis, I get this difference of NA and B. Remember that J3 was the difference of the number of operators. And since J3 is that difference, I can rewrite K squared as J squared, or J3 squared minus 1/4. So K squared is proportional to J3 squared specifically. Further, K3 on this basis is the sum of these NA plus NB. Remember that NA plus NB was J. So I get J plus 1/2. So if I'm talking about a shared eigenbasis, since these are normal and commute, then I talk about the eigenvalue of K squared must be restricted as M squared minus 1/4 if it is to be connected with standard angular momentum. And the eigenvalue of K3 is J plus 1/2 to be connected with standard angular momentum. But this restriction right here is exactly the restriction of the discrete half-integer classification of the unitary irreducible representations of a Lorentz group in 2+1 dimensions. That's a bunch of word salad to basically say this is something that's well studied and realizable. Our SU11 operators, our hyperbolic angular momentum operators, are a specific classification of a well-studied algebra. Thus, we can realize this as a representation of the Lorentz group in 2+1 dimensions. Now we want to apply this to addition of angular momentum. And this specifically is for Philip. This project originated with a question Philip asked about the bounds of total J in addition of angular momentum. We're going to give a proof of that without counting. So consider two systems of independent angular momentum, and we fix them with a J value. So I'll let the first system have these operators, the second system have these operators. This is a personal notation just to define what system they come from. And then total J, I'm going to give as the sum of those vectors, those operator vectors, and J squared to be the dot product of them. And each individual component of this J is just the sum of J1 and J2's components. We now consider a tensor product basis on these two. When we did two harmonic oscillators together, we considered their product basis. Here we'll construct a product basis. And we have another basis that our operators can act on. This is called the coupled basis. And I'm going to drop J1 and J2 because they're fixed. This is a common physics convention. Total J squared acting on this can be shown to be J times J plus 1 acting on the state. And J3 can give M. So it's like just one angular momentum system, but we're doing it for total angular momentum, the combination there. In general, for the representation space Vj of a fixed value of J, then the product of the representation spaces can be decomposed like this. So these are product of irreducible representation spaces of SU2, and it decomposes into different dimensional representations. Where the dimension of each space, like I said earlier, is 2J plus 1. If we let J, capital J, label the irreducible representations over here, then we see that the total J is bounded between J1 minus J2 and J1 plus J2, where we're assuming J1 is greater than J2 without loss of generality. That's not the case. Relabel J1 and J2. Typically, this is just presented, and the standard argument is a counting argument. We'll give a visualization of this first. I'll take the simple case of J1 equals J2 equals 1/2. So this is a 2x2 system. On the left side, we have this product space. So fix M1 1/2, M2 minus, or M1 minus 1/2, same with M2. And I can show that equivalently, these go to the coupled basis. So this is J equals 1, M equals 1, M equals 0, M equals -1, J equals 1, the sum of them, J1 and J2, J equals 0, which is the difference of them. This can be done for any size of J1 plus J2. I just picked a simple case. Our standard argument, we're going to note, the product of spaces gives the product of dimensions. The direct sum of spaces gives the formal sum of dimensions. So the standard argument is that if the left side equals the right side, the dimension of the left side should equal the dimension of the right side. That's specifically given as this sum right here. If you compute it out explicitly, which is done in the thesis, you'll see that this is true. However, this doesn't really satisfy us. This is a counting argument. We already assumed what the bounds were and showed that they were true. We want to derive the bounds algebraically. So first, we're going to use the Schwinger basis to construct addition of angular momentum and then give the proof. When we represented angular momentum, we used 2 harmonic oscillators. So 2 angular momentum is going to have 4 harmonic oscillators. My J1, M1, J2, M2 are going to be labeled as NA1, NB1, NA2, NB2. They'll each have, of these 4 oscillators, their own set of operators. Each independent J, J1 for instance, is NA1 plus NB1, or J2 is NA2 plus NB2. Same thing for MI, NA1 minus NB1, or NA2 minus NB2. And we're going to consider the following system of operators. M plus, M minus, and M3. Note specifically the eigenvalue of M3 on the coupled basis is J1 minus J2. These can be shown to satisfy the commutation relations of SU2. Similarly, I'm going to define this tilde basis, this Q tilde basis, of Q plus, Q minus, and Q3. And note the eigenvalue of Q3, J1 plus J2 plus 1. And these can be shown to satisfy the defining commutation relations of SU1. So I can rewrite my total J squared in terms of these. It's a long process, but this is done in the thesis. And then use this to get my bounds. J squared, if I process this out in the M construction, gives me that the eigenvalue of J squared is bounded below by this construction right here. That doesn't tell me specifically about J though, but what I can argue is that J is positive, J plus D plus 1 is positive. And since this product, after factoring out, has to be positive, J minus D is positive, so J has to be greater than D, the difference between these two. Similarly, I can get that the eigenvalue is bounded above by this product right here, processing it out in the Q realization. And then similarly argue that since this has to be positive and I factor out on the left side, the sum of them minus J has to be positive, so the sum has to be greater than J. Putting these two bounds together, I get that J is in between the difference and the sum, so we get the exact same bounds derived algebraically without having to use a counting argument. This isn't given in standard physics literature, and no full proof of this was provided by Schwinger, so this is the first full proof that I've seen of this argument. We're currently actively searching for a visual proof of this construction of the bounds here, but it's eluding us probably because we're dealing with like basically a 4-dimensional system with 4 different oscillators. Now for some remarks and conclusions. First, a summary of what we did. We represented angular momentum with harmonic oscillators. This gave rise to a hyperbolic angular momentum, and we can use this to give the algebraic derived bounds of total J. The SU2 ladder operators that we constructed ladder within a representation, an irreducible representation of SU2, and they ladder between irreducible representations of SU11. SU11, their irreducible representations are labeled by M. This is something shown in the thesis. And SU2's operators are labeled by J. So they're laddering in between each other, almost like a giant lattice within some sort of larger algebra. probably something along the lines of SP4R. Future directions would be to explore the algebraic and geometric structure of this relationship. In the thesis at the end of chapter 4, I believe, I introduced some interesting mathematical observations that hint at a deeper significant structure. We want to connect this with loop quantum gravity. This project came from a research lecture study group that I started, the SIU quantum gravity group. And this came up when we were studying loop quantum gravity. This was a question brought up by Philip specifically. How do we know what the bounds of J are? Shajesh was aware of this paper that gave these bounds, and then we went from there. We also want to derive a horizontal ladder operator like a K plus, but for addition of angular momentum. There's the equivalent of J plus and J minus in addition of angular momentum, but no K plus or K minus. I want to acknowledge specifically Shajesh and Prachi, who over the past 10 months have grilled me on this material to the point where I know absolutely everything in that thesis, front and back. Dr. Kochik, who has a beautiful knack for being able to think of anything visually, it doesn't matter what it is. And of course, my wife and my cats, who kept me level-headed throughout this entire project. And these are my sources.
We can start with questions. After that, Jackson wanted to take a picture of it, everyone together. And then it has to be a closed door committee alone. Again, because Jackson will fit. The question, please.
Yeah, it's a lot of stuff.
What sort of experiments could you, design? Just kidding.
No. We've talked about this before. This probably is a problem for Lance. Lance, the angular spin is related to magnets. We talk about magnets. Thane, you don't do experiment, but you help Lance out with this. So this is a job for Thane and Lance.
Then would translate it into something that matters. Well, it matters to me, and then I'd try to figure out how to make that exist.
Some sort of experiments that show that space-time is discretized would be important. Like, so this is connected to discretization operators in loop quantum gravity. The structure yields spin networks, those yield those operators. So if someone could design an experiment that shows that space-time is discrete rather than continuous, that would be the goal.
In quantum optics, these groups are studied, and even the K operators, they use SU11, they don't use the specific representation here.
You
But
can
this is-
take pseudo Hermitian operator, and it's many people study same structure as you want. So I think loop gravity is, I don't know loop gravity, but you can easily realize your system with artificial lattice or pseudo Hermitian operator. It's a current topic of physics.
There's one thing that this interestingly hints at, which is possibly like a lattice gauge theory type of thing. So this hints at some sort of gauge invariant on a lattice like this. And that's used properly in like quantum chromodynamics, certain theories of quantum gravity. That's where that's seen. Yes.
Yeah, I mean, some people in contribution textbook. What is your contribution?
What is my contribution specifically?
Yeah.
So, two things specifically. Here's the clicker. There is no full proof of the algebraic derivation of the bounds. Schwinger in his paper tells you this is it and this is it, but he doesn't fully derive everything. He doesn't even, let's see. Like these, he doesn't even prove that this is true. He just says this is true. So we went through and we proved this construction is valid. And then we went through and proved fully, like all the way through the process. So that's one thing. But more specifically, the big thing is this visualization. I talk a lot, wow. Okay. Let's see here. This visualization is nowhere in literature. So this is something that you're presented, it really motivated the whole project. So there's no like visualization method for constructing these operators. And this gives a very, very nice way, almost pedagogically, to construct this system rather than using algebraic techniques.
Also, one of the goals was to get a visual proof for the bounds on J, which we think is possible, but we have not succeeded yet.
Another goal would possibly be to use this for a method of deriving Clebsch-Gordan coefficients without using orthonormality arguments for the mixed states.
Okay, I'm going to look at the text for evidence. Supply on section talk about single representation, but
He doesn't, in his Schwinger representation, he doesn't talk about the hyperbolic structure. He only uses it to introduce like rewriting ladder operators to then do addition of angular momentum, which is really useful. That's where I got a good bit of the material for addition of angular momentum in the Schwinger basis. Any other questions?
Was there anything surprising you found that you didn't expect to find?
I think one thing that's really cool, at least to me, is that these two sets of algebra interact with each other. Like one goes basically up and down, one goes left and right, for example. But they like go with each other. So one can only go up and down given the other one like this. So like if this is one algebra and this is another algebra, this algebra can only go up on the other algebra. Like they climb up and down off of each other. And they exist within some larger algebra. Typically, this is realized as SP4R, which has a nice realization as four harmonic oscillators together. It's called the metapleptic realization. That means like in classical mechanics and quantum mechanics, there's talks about how the symmetry works between those. So if you realize the symmetries of those on four harmonic oscillators, it's the embedding of that into SP4R. So it's a really useful thing. I want to delve more into that because I think that hints at the full structure of it. And then another interesting thing, which I didn't talk about in this presentation because there's not like proofs for any of it, I just like more or less conjectured it, is there's a really interesting correspondence between specifically K3 and J3. They don't get constructed very nicely with the Jordan map, but if I introduce kind of like a way to multiply them in each other's spaces, it reproduces them perfectly, which hints at, again, the interaction of these two algebras nicely. Ian.
So I'm gonna ask something I'm not sure is valid, but maybe you could help me out. So you have in B and in A.
Mm-hmm.
So I'm just gonna generalize the axes. Let's say that in B is Y and in A is X.
Yeah.
Could you have like an in C, like
That's
coming out?
yeah. So that honestly probably is what's going to happen in a four-dimensional case. Our idea is that we're taking in 4 dimensions. We think we could take two of these and stack them on top of each other and get like a grid in the middle. But if I had like 3 oscillators, for example, one would be along the z-axis, and then I'd have like z greater than 0 cubed being my lattice grid here. Or yeah, I could generalize it to any even more dimensions. It'd be hard to visualize it, but yeah, it would be just the non-negative integer grid in that dimension. So here it's in 2. If I extended it in 3, I'd just get like the first quadrant of R3 as integer dots. If I did it in 4, it'd be the first quadrant of R4 with integer dots. All right,
We have not had a physical representation of 3, but 4 is the addition of angular momentum. So we have to go to 4. 3, we don't have a clear picture of what it could be useful for.
So it's possibly something like position states or something like that, but I'm not entirely sure. That might lead to, for example, like I know Harsha works with like the entropy of lattice grids, and that typically is a 3-dimensional lattice. So maybe this would be a way to construct that from this mathematical realization. Yes.
So like general angular momentum is like a bread and butter for a lot of quantum applications,
Mhm.
right? So where does hyperbolic angular momentum comes in?
So like Shajesh said, this is useful in quantum optics. They talk about SU11 a lot, but more so for me, what I'm using it for is the representation theory aspect. So this is both a math and a physics thesis, and I'm more so talking about the mathematical structures because it very cleanly algebraically produces the bounds on total J. Physically, there's probably other utilizations for SU11. For instance, it's isomorphic to SO21, which is the algebra of the Lorentz group in 2+1 dimensions. So some sort of relativistic relation would be there. I know this is sometimes used to create what are called relativistic spin networks, which are spin networks labeled by the eigenvalues of the Casimir invariant of a Lorentz group representation. So probably some sort of relativistic thing is going on here, but it's used in quantum optics quite often.
Again, hydrogen atom can be written in terms of SU11 and SO2, SU2. So hydrogen atom surely will have this. We haven't done it, but it will have. Take it as SO4. Any more questions? Otherwise, let's thank Jackson again.
You want to do the picture now, or everyone go outside and those that want to be in the picture come back in after we deliberate?
I think we do it now.
Do it now? Sounds good.
Outside or here?
Yeah, Nicole. Oh, that's a good point. There's a lot of people. We might have to do it outside.
Yeah.